Alrighty, Rich, why don't you go ahead and take it away?
All right, thank you. Is my audio okay?
Yep, sounds good.
Fantastic. All right, well, thank you so much. Yeah, my name is Rich Pesky. Just a little background, I work with Wildan on the California Energy Design Assistance Program. We call it CEDA. It's across the state of California on behalf of the investor-owned utilities, PG&E, Southern California Edison, SoCalGas, San Diego Gas and Electric. Our mission, Wildan's mission in that area is to help communities transition to a low carbon future. My background is in architectural practice, and over time, I've been lucky enough to direct my work towards sustainability, and now more recently with Wildan, focused solely on decarbonization, electrification, and energy performance in our built environment. So, I'm going to skip reading the course description and the objective slides here, so we'll have more time for the content that'll get us to the objectives. And then, like we mentioned earlier, we'll try to leave some time at the end for questions or discussion. But I will pause here to say thank you to AIA East Bay for providing the continuing ed credits, and thank you all for being here. I'm glad to be back here with this chapter and maybe a few of you from my last time last year. So, here is the agenda. So we're going to be thinking about decarbonization, and we'll start with goal setting in the design process and around decarbonization. Then we'll move into the bulk of our presentation, looking at a range of high performance measures and why they're important to decarbonization. And then we'll close it out with some thoughts on evaluating these or any other measures and how they can impact the operational carbon of your buildings and whether or not they're the right ones to align with your goals. So let's set the stage around decarbonization. Nothing new here. Decarbonization has become an urgent matter. And likewise, many of you have seen numbers or charts like these before. And before we get into the components of a low or zero emissions building, we first have to look at the breakdown of carbon contribution from our buildings. So on the left, you'll see that buildings account for about 40% of all the carbons emitted globally. And then if we break that one slice down, on the right, then we're seeing how that breaks down between embodied carbon and building operations. So 28% as embodied energy in materials and construction, and then 72% about in the operation of buildings. Something interesting to keep in mind with this conversation, the built environment in square footage is expected to about double by 2060. So if we think again about the carbon impact of our buildings, that's a huge opportunity. And well, for us in this industry, and an equally huge responsibility to do what we can for decarbonization along the way. Okay, I'm going to go a little bit into history here. I think this is really interesting. So, operational carbon comes mainly from our building's energy use. Today, electricity and natural gas mostly, and renewables. So, I think this is a really cool timeline of where that energy has come from throughout the history of the United States. Starting mainly, let's see, over here, 17, 1800s, renewables in the form of wood, which isn't something most of us think about today. Then coal in black starts eventually taking over, and other sources coming in mostly in the 20th century. And then over time, coal shifted from a point of use direct heat source, burning in your house, to electricity generation. And then in the last 20 years, so this is like, the very far right side of the chart here, the big change has been a big drop in coal and an almost equal increase in natural gas and that steady rise in renewables down here in green. So, of course, this is US data. So California is going to show those renewables rising much more rapidly than the national average. So good on all of you. But things are changing. And in those renewables, we've got our buildings being served by increasingly lower carbon energy sources. This is another look. So this slide only shows coal in black and wind in blue. And this goes from the year 2000 on the left over to last year on the right. I wanted to show this to highlight something really cool that happened a little over a year ago, which was the first month, this is again US data, first month where we as a nation had wind energy surpass coal energy for the entire month. Uh, I think that's awesome, and I'm super looking forward to seeing more of those kind of metrics and more of those trends continue. Another little slice here. Of course, we know things are changing here in California, and you really just need to look around as you're driving down the road, see all the solar on rooftops, all the wind turbines out there in the open areas. Um, Solar has gone, so solar is bright yellow up toward the top of this chart. It's gone from negligible in the middle, 2010-ish, and just exploded throughout the 2010s through today. Um, California has had a strong wind generation capacity as well. So the green up on top is wind. And that's grown steadily over the years. And it's that increase in renewables that helps drive decarbonization at the scale of the grid. Now, a lot of that PV, the electricity in yellow, a lot of that PV is on the scale of individual buildings, but it still adds up to drive our overall push towards decarbonization. Then one more little slice here. Yellow is solar again, and this is taking not a years long look, but a 1 day look at how solar comes to play. That from midnight to midnight here, uh, there's of course no solar during the evening or the nighttime, but then during the middle of the day, there's a huge jump in solar. Um, and then in the evenings and the morning, we have to rely on imports and fossil fuels to make up that difference. There is battery storage growing. And what this tells us is decarbonization strategies, measures, systems that we're implementing in our buildings. What we choose and how we use them is really impacted by the time of use, since the electricity coming off the grid during the day is largely solar and low carbon. So it might drive a discussion of when we're using our energy to decide which types of measures we want to hit. All right. So that sets the stage for some of the bigger picture views where our energy comes from and where it's headed and what's fueling our buildings. But let's shift that then from the larger scale into building design and the work that you all do as design professionals, and that my team honestly has the privilege to help out with where we can through the energy design assistance work that we do and other opportunities. So we'll talk about how one might approach a project, or even how you might approach these decarbonization goals at a firm level, and how we get started with that. Okay, so a lot of us have been working with and talking about energy efficiency for many years. And thinking back through my own career, which might parallel some of yours, maybe we just started with an idea to conserve energy, conserve our resources, use them wisely. Maybe we wanted to bring down the operational cost of a building, and maybe we were able to work on a lead project here and there. Uh, might have had some clients that were starting to look at payback, for instance, for whatever options were on the table. So net zero then came into the discussion some time ago. And what's been really interesting for me is to see how the concept of net zero shifted over time from net zero energy to net zero carbon now. And honestly, it was surprising to me as that shift took place to see how much of an impact it had on the types of measures and the systems we'd consider. Energy and carbon are two different metrics related, but they may drive different systems. So, but even if we don't hit zero carbon, and for many of our projects, that's just not going to be a reality, the urgency of decarbonization and the impact of what we build on the environment, on our climate, it brings many of us to place decarbonization as one of, if not the primary goals. And then we can consider the rest of these goals after we look at carbon emissions. So I mentioned that the definition of net zero has changed over time, and it might still vary quite a bit depending on who you're talking to. Not long ago, the Department of Energy set out to formalize the definition of zero carbon, specifically zero operational carbon, so that we all had a common definition across the industry. They laid out three foundational blocks for achieving that, which you can see on the screen here. First one, we focus on energy efficiency, which is great because a lot of us have been focused on that for a long time. Then second, we're not burning fuel on site. Usually that means natural gas. And honestly, that was new for me and probably a lot of you. I mean, a while back, of course, we'd use gas for heating and cooking. You know, it's cheap, and we were speccing efficient furnaces and boilers, right? But even that now has changed. And then third, once we've got an efficient building and ideally not burning fuel on site, now we're powering what's left solely from clean energy, whether that's through on-site generation or contracting for clean energy or using on-site energy storage or some combination of those. But even if we can't make on-site generation happen, we do have a grid that's moving steadily towards lower carbon. Okay, so we've set our goals and we have a definition of what zero carbon means. What other resources might we have as we move further into design? Um, Energy codes have given us everything from direct requirements to a variety of stretch codes. The standards are consensus built. Some of you maybe actually be involved in that with the input of industry leaders like AIA and sometimes many of us. But the goal here is to identify feasible and realistic strategies we can use toward better efficiency, lower carbon, and improved building performance as a whole. So another resource is to look at some target EUIs or energy use intensities as a goal or a starting point. The chart that's on screen here, this comes from the New Buildings Institute, their zero energy commercial building targets. This shows targets by building type on the left, and then how that plays out in each of the IECC climate zones, which puts us here in California, generally the threes and the fours. And then depending on where your project is, if we look at, say, a small office, now we're in an EUI range of 16 to 18 as a target, and again, EUI KBTUs per square foot per year as a measure of the building's relative efficiency. So those values give us a target to shoot for as a very efficient building before we start to layer in renewable energy. These values might seem aggressive at first, but I can say from the projects we've looked at across the country, they are achievable. One more resource they've got, NBI, is a database of emerging and verified zero energy buildings. So in this tool online, you can filter by location, building type, the status of the projects to see what comparable projects might be hitting for EUIs. They got a number of other resources online or for download, and that includes case studies if you're interested in the details of some of these projects. Uh, so what measures did they adopt? How did it play out? What factors did they consider along the way? So there's a lot of information out there. And then at a broader scale, you can see the ranges of EUIs for each building type, what the medians look like, the highs, the lows, the outliers, which is all a really great resource because it helps us see the target and how achievable it might be for a comparable building that we might be working on. This is a national database, but as you can see here, California is representing really well as always, which is totally cool. All right, ton of other resources out there with a lot of attention being paid to decarbonization. I'm not going to go through all these, but it's just a little slice of what's out there, and these resources keep growing honestly, through your efforts, through AIA, through members, organizations. So keep at it. The last one here, utility programs. That's the world that I live in. California's got this covered, and if you're working in other areas outside of California, you can always check online and see if there's any utility programs for some type of free design assistance or incentives, rebates, things like that, that you can layer on top of whatever your firms are already doing. So all these are solid resources, anywhere from just learning a little bit more to helping you set targets, down to just trying to figure out what has the most impact for your specific project. So as we wrap up the section on goal setting, I just wanted to circle back where we started. And if you remember really nothing else on this, keep this in mind. Start by making your project as energy efficient as possible. Eliminate on-site emissions wherever possible. And then only after you hit those two, then you top it off by using clean energy to make up the balance. And honestly, it is a balance. Keep in mind that the more efficiency you build into the base design, the less energy you have to procure to pull in, or the less solar panels you have to put on top. All right, so let's move on to the next part, high performance measures. And for a start on building envelope. Okay, so the building envelope is a key focus for any efficiency goal. No surprise there. Without a good envelope, you'll need a bigger mechanical system just to make up for it. And that poor building is going to spend the rest of its life fighting harder than it had to just to not waste energy. So insulation, thermal mass, air sealing, those things are now in codes. Not just the air barrier, but testing it now to make sure it's doing what it's supposed to. And this is where you as architects can really make a difference through detailing all of those openings, excuse me, all those openings so that air tightness isn't relying on whatever the contractors felt like doing that day. Um, on the code side, right? So this shows from 2004 on the left through today-ish, how over time the code U values for the envelope, wall and roof here, have come down with, of course, lower U values, meaning less heat energy lost through the envelope. So the codes get more restrictive, we can still push that further. Then the same for windows. The code over time drives lower U values for glazing, meaning generally we need to be speccing higher performing windows. And luckily the industry is somewhat keeping up. So even with what the code requires, we may still be able to go above and beyond. Okay, so there's just throwing these out there. There's a few glazing options on this page that have come into our toolkit over time. Vacuum insulated, super cool if you want to look into that offline. If you haven't seen them before, they're very thin, they're very efficient. It's actually really cool for like historic preservation stuff where you can't do double pane, normal thick double pane glass. And then, okay, so electrochromic switchable glazing. It's another really neat one. You can vary the tint. You can, in some cases, make it opaque, which allows you to reduce solar heat gain at peak times, and side benefit, reducing some glare for the users or the occupants on the building comfort side. And then last one here, triple pane, really ramping up those R values, bringing down the U values. These have potential to reduce daily energy consumption 20 to 25% in peak demand, which, let's see, yeah, we've got that shown here. So peak demand reduction goes way up with these kinds of glazing opportunities. All right, so let's move from the envelope into mechanical, and we're going to look at some opportunities for efficient electric heat. So now, as we shift our focus from the architectural side to mechanical, we'll look into kind of a significant transformation in heating technology, and that's the transition from that gas heating that we talked about earlier to heat pumps. And understanding why that shift matters is honestly, it's crucial for both sustainability and energy efficiency. So the shift from gas heating to heat pumps is more than just a trend. It's really about addressing climate change. And heat pumps are highly efficient systems that, if you're not into this, they transfer heat rather than generate it through combustion, which means they use less energy, a lot less energy compared to traditional gas heaters. And that efficiency translates into lower energy bills and a significant reduction in greenhouse gas emissions. And thanks to some pretty cool breakthroughs in heat pumps, they're really starting to shine, even in those chilly, cold climates where you think they might struggle a bit. Um, Heat pumps, a little bit of technology here. I'll be honest, when I first started my career in this field, I was a bit confused by all the different configurations heat pumps come in. You can see some of them listed on the left there: air source, air to air, air to water, all of those different combinations. But if you basically follow the construct in the first bullet point up there, blank to blank, the first blank is the source you extract heat from, and the second will be the heat sink, or where you're transferring your heat to. So the blank could be air, ground, or water. And to talk a little bit about the different combinations there. So if everything else remains the same, each of those systems will have, you can see it on the picture here, an evaporator, a compressor, a condenser, and an expansion valve. Off the off to the other side, then we've got 6 different types of heat pumps. Dual fuel heat pumps combine a heat pump with a traditional furnace. Happens to be what I have in my house. They use the heat pump as the primary heating source, and then the furnace kicks in during extremely cold weather if the heat pump isn't designed for those temperatures. And that makes sure that the system optimizes performance and efficiency. So that would be a good option for existing buildings, as you can integrate a heat pump with an existing gas furnace if it has one. And then, of course, you'd need some help maybe from a mechanical engineer to figure out the compatibility of that existing system with the heat pump. Um, then just down there at the bottom, absorption heat pumps, I won't get into it, but they operate differently than the standard electric driven types. Instead of a compressor, they're using a heat source like natural gas or solar energy to drive the refrigeration cycle. These systems, they're less common, but they do have an ability to use waste heat or renewable energy sources, which can be a very cool option in some cases. I do want to call this website out, a little plug, website slash YouTube channel. If you want to know more about heat pumps or honestly any mechanical systems, I have spent a ton of time on Engineering Mindset's YouTube channel. They have some really great basic videos about how heat pumps work, or how does a VAV system work. So if you're not connected to that already, check it out if you're interested. It's a pretty cool rabbit hole. Okay, so one more graph for you here. This one shows the carbon emissions per unit of heat at different temperatures. And the wide bands reflect the varying efficiencies for different types of equipment, which are listed down there at the bottom. ASHP is air source heat pump, blue is ground source heat pump, yellow is fossil fuels, and the pink is ground source heat pump and cold climate air source heat pumps. So the as you can see, the yellow fossil fuel has a constant emission factor regardless of the outdoor temperature, right? You burn gas, you get energy out of it. The green cold climate air source heat pump, using grid average emission rates for the region, that produces less emission for the heat it generates down to about minus 10 degrees. And then it starts going up because there's not as much heat outside to grab and transfer into the building. The blue, the ground source heat pump, steadier because the heat source is the relatively constant temperature of the earth, below the surface. That's more efficient than the cold climate air source heat pump until about 40 degrees above zero, when the air starts having more heat than the colder earth. And then, like I said, peach is either an air source heat pump or ground source heat pump when powered by zero carbon renewable energy. So if you're using zero carbon energy, either off your site or off the grid to power a heat pump, you're not going to be generating any carbon at all or emitting any, which is awesome. All right. So VRFs, heat pump VRFs. These are like the sophisticated cousins of traditional air source heat pumps. Instead of a single outdoor unit pushing air to all parts of a building, the VRF uses multiple indoor units connected to one or more outdoor units. And what sets them apart really is their ability to vary the flow of refrigerant based on the specific needs of each indoor space. So if you picture this, a large office building, one part of the building might be, bustling with a lot of people, maybe a conference room. There really needs some cooling. Other part of the building might be on the shady side of the building and quieter. They might actually need some heat on the same day. So VRF systems, they can handle that with precision. They adjust the refrigerant flow to each area to make sure that they maintain their ideal temperature. And that not only enhances comfort, but it also boosts efficiency and minimizes energy waste. I mean, sometimes you're pulling heat out of one area of the building and pushing it into the other if that's what the building needs. So, unlike traditional standard air source heat pumps, which often provide a uniform temperature across the entire building, these ones can really tailor climate control to down to the zone level, even better than the other systems. And that can be better comfort, better energy savings. They really are starting to become a more popular choice for larger, complex buildings where they need to handle all those cases. All right, heat pump applications. Not going to read through all of these, but if you're thinking about heat pumps for various building types in any climate, it's really important to understand how the different systems perform and the challenges that might come with it. California ranges from consistently temperate areas to areas that are cold in the winter and hot in the summer, which really does impact heat pump choice and efficiency. So you can work with your mechanical engineers or look up data like this online. Again, I'm not going to read through every application for every configuration, but just understand that, say, a water to air heat pump might work great for one building type, but might not be the best choice for the next building you're designing down the road. So, take some rules of thumb with a little bit of caution there. Okay, so heat pumps compared to gas heating. Picture you're working on a project, you're sitting there with the mechanical engineer, or maybe they're not even on board yet, and you're thinking, okay, we're considering our options here. We're at a crossroads. We're trying to decide heat pump or gas heat. If we walk through those two choices, we can kind of see what they have to offer. So on one side, we've got heat pumps. Let's call them the eco-friendly superheroes of heating. They are incredibly energy efficient, often using less energy to move heat around than gas furnaces do to generate heat. And that efficiency translates into cost savings on your utility bills, especially if you're using them for heating and cooling. And then, speaking of savings, heat pumps come with significant environmental benefits. Since they don't rely on burning fossil fuels, they produce fewer greenhouse gases, making them a greener choice. Plus, their dual functionality means that they can heat and cool your building or the space, meaning more year-round comfort for one system. But they do come with some upfront costs, coming down over time, but they do come with some costs that can be higher if you're installing them over a traditional gas furnace. And when it comes to extreme cold, they have traditionally struggled a bit. In frigid temperatures, their efficiency does drop, as we saw in that chart a little while back. So sometimes they need a little supplemental heating. And then since they run on electricity, they do contribute to added electrical usage, which can be a concern in areas either with high electricity rates or with high carbon grid sources. Not as much of a problem in California, but if you're working elsewhere, you can look up online and see in general terms what the carbon emissions factors are for that area's grid. Okay, so let's say you're now considering a heat pump and you're thinking, okay, energy efficiency, environmental benefits. Be wary of those challenges, cost, extreme cold performance, electrical usage, but there are ways to smooth out some of those bumps. So cost mitigation. The initial investment can be a bit of a hurdle, but there's a silver lining on that. Most regions still offer incentives and rebates to make them more affordable. There's local utility rebates. There have been, and in some cases continue to be, federal programs for it or state programs that can do some work to reduce your upfront costs. There's financing options that let you spread out the cost over time. And then thinking about the extreme cold performance. Technology can be your ally in that. The modern cold climate heat pumps, they do operate more efficiently in frigid temperatures, um, meaning that your building can still stay comfortable to a certain temperature. And if it gets exceptionally cold, then we can design in some supplemental heating for a backup. And then lastly, electrical upgrades can optimize your system's performance. So system assessments by your engineers or other partners can improve energy efficiency around the building, even things that you can do like better insulation and windows. That can reduce the overall load on the heat pump, making it work more effectively and saving even more on those electricity bills. So while there's challenges to adopting heat pumps in some cases, there's also practical solutions. And I just want to plant that seed in your mind in case people start to disregard them on some of your projects. Okay, we're going to move on to domestic hot water as another area where there are newer high performing measure options to pick from. So water heating, it really comes down to that same story of gas versus electric. But instead of HVAC systems, now we're pitting our heat pump water heaters against our traditional gas water heaters, or electric resistance water heaters if that's on the table. But the story is the same, really. So if we dive into heat pump water heaters, if we called heat pumps the eco-friendly superheroes of heating, we can call these maybe the sustainable sidekicks of hot water. So the heat pump has really the same main parts as a heat pump. They've got the evaporator coil, which grabs heat from the air, the compressor, which boosts that heat to a higher temperature and pressure, a condenser coil, which then transfers the heat into the water. So it's like a high-tech heat extraction machine, but for hot water instead of the air. So why is that better than traditional gas or electric? I mean, it still just comes down to efficiency, to be honest. Heat pumps are way better at using the energy they get because they're moving heat around rather than generating it from scratch. That means that they can use just a little bit of electricity to move a lot of heat from one source into the water, which, I mean, in some cases, that can make them 3 times or more efficient than gas or electric standard water heaters, which, I mean, 3 times the efficiency is pretty amazing. What kinds are there? If we start, like there's the integrated heat pump water heater, little diagram on screen here. It looks sort of like the water heater you might have in your house or in the closet of your apartment. This one is simple and compact. It's all in one. It's got the heat pump and the tank combined into one single appliance. Um, it's so it pulls heat from the nearby air and transfers it directly into the water in the same unit. This is really at its place in settings where space is tight. Smaller homes, apartments, even utility closets where you don't have room for separate units. But the compact nature makes it super easy to install and a lot less intrusive than some of the other options that we'll look at. And with everything housed together, you're avoiding that complexity of, having to run separate refrigerant lines and installing multiple components. So the central heat pump water heater, little diagram on the right there, it takes all of those heat pump components, the tank, the heat pump itself, the refrigerant lines. It's kind of like building it on site. It's more complex, but it offers flexibility and scalability. So you have a separate heat pump unit that extracts heat from the air, and then that's transferred to a dedicated storage tank. There may be swing tanks that pull hot water in and out depending on the time of the day, or to help with peak energy concerns. And with all of that, it does the same thing, right? It's pulling heat out of the air, transferring it into the water, storing it for use, and sending it around to the building. It's it's really at its home in larger buildings, larger homes, maybe multifamily buildings where you need a lot bigger water supply and the space is a little less of an issue. They can be, they can require an extra room in the area of the building. But if you think about it, whether you choose an integrated heat pump water heater for that compact convenience or a centralized system for scalable performance, they both offer significant energy savings over the other options. And again, integrated systems, tight spaces, straightforward installations, centralized is more about flexibility and efficiency for bigger scale systems. And then, all right, so outside of efficiency itself, I do want to touch on refrigerants for a minute because it has become part of our decarbonization toolkit. What we're looking at with refrigerants is that each different kind of refrigerant has a different global warming potential, or GWP, attached to the refrigerant itself, which is the gas slash liquid that flows around inside the heat pump systems. So if we start a little further back, 15, 20 years ago, most of our systems were using R22, which was widely used in air conditioning systems. R22 was banned a while back, largely to protect the ozone layer, if any of you remember that. And we switched to R410A since the ozone depletion potential was a lot less. Um, then fast forward to today, the focus shifts again. We're now moving away from R410A, and really this is why it's all about reducing our environmental footprint. So in December 2020, the AIM Act that you see there in bullet point number 2 was signed into law, which phases out the use of HFCs, which are potent greenhouse gases contributing to climate change. And then under that act, the EPA at the time set a big milestone that said starting January 1st, refrigerant with GWP over 700 would no longer be allowed. So the higher the GWP, the global warming potential in that refrigerant, basically the worse it is for climate change. The more heat it retains in our atmosphere. So why is that a big deal? Environmental impact, yes. These lower GWP refrigerants have a much lower impact on global warming compared to their higher GWP counterparts. And if I didn't say this earlier, like the reason this is important, you're thinking, wait a minute, it's a closed system, right? So what does it matter what's inside it? They do leak. And honestly, there's tools online that you can use to assess average leakage for different system types, and assess, excuse me, how much of any refrigerant can be expected to leak into the air over the life of the unit, or at the change out of a unit to another one. They do their best to try to capture those refrigerants, but some does leak out as they're disassembling the systems. So that's a problem. Using lower GWP refrigerants helps with the ongoing emissions of any leakage, as well as avoiding penalties along the way and making sure our systems meet the latest standards. Performance, the lower GWP refrigerants can vary in performance, but overall they do perform efficiently. So advanced technology with the systems also means that these still can provide excellent cooling and heating performance while reducing the overall environmental footprint. So then, as we transition away from the higher GWP, global warming potential refrigerants, and start to embrace the lower GWP options, we are making a positive impact on the environment. Now, I realize a lot of this happens on the mechanical side, and I'm guessing a lot of you are architects, but having this knowledge, keeping this as part of your toolkit will allow you to ask those questions on, your engineering coordination meetings to say, hey, wait a minute, cool system, but what refrigerant is it using? Is there anything we could do better that's out there? These the refrigerants that are available and the systems that use them, these are like they're changing daily, to be honest. If you ask an engineer or even a equipment manufacturer or supplier about like what's out there, what's best right now, ask them again a few months later because it could change. Don't just assume that something that was terrible last year might not be very different this year. I've listed some of the refrigerants here on this page. Again, not going to read them, but the key point here is, looking at R410A on the upper left with a GWP global warming potential of over 2,000. Those ones down at the bottom there, which are in production and used in some of the systems we're speccing, compare 2,000 to 1, and you can start to see that this can have a big impact. Cool. Okay, so we did some comparison of overall emissions with the different refrigerants, and I it's a little bit of an eye chart in terms of like for the global warming potential here on the left, where you're seeing blue as R410A, orange as R32, and gray as R54B, a lot of numbers and letters here. Global warming potential goes down as we move to the right. The system capacity and efficiency can be kind of similar. The refrigerant charge may be a bit less with R32 than some of the other ones. And jumping back up with R454B. Lifetime emissions, this is what I mentioned, right? If you do the math, if you use the tools that are available online, you can see that lifetime emissions between 410A, R32, and 454B, they do come down. One of those factors is indirect emissions in kilograms of CO2, and then direct emissions, meaning how much does the leakage matter. So not going to get into the details of that. Just keep in mind that there's a lot of different ways you can look at this stuff, and there are resources out there that can help you consider it. So I do need to point out, I like to mention this. So global warming potential is one of many factors, right? And choosing your refrigerant can be affected by other things. Like, is it available in the system I'm looking at? How toxic is that refrigerant? Is it flammable? Ozone depletion? All of these things. Like, so I would never say that you should choose something solely on GWP, but I would encourage you to consider it strongly with all the other factors. Okay, so equipment loads. We're going to look a little bit at some specific plug loads or end uses that might have an impact on the carbon emissions of your building. So I'm actually going to start all electric commercial kitchen. We've looked at a few projects now with a lot of kitchen equipment in them, and I can say that there are electric options for all common gas equipment. There are some like specialty items where they just don't have electric equivalents for them yet, but in many cases you can. Induction cooktops. I mean, these are super cool. A few years back, I actually happened to find like an induction hot plate, just, the little one burner ones honestly, at Goodwill. So of course I bought it because I wanted to try it out. And honestly, they're amazing. Like even that little, standalone one burner one was heating up water faster than my like big, really nice gas range. And I eventually replaced the gas range with an all induction cooktop because it worked so well. So if you haven't tried them, totally give it a try. They're not quite embraced by a lot of chefs yet, but that's starting to change. They're like really controllable and they work really well. So I wouldn't be surprised if that changes in the future. Might still be some hard sells out there, but basically we're using electricity through induction. I mean, that's a whole electrical engineering course on its own, but it's basically like using electromagnets to excite the molecules in the pot or in the pan rather than just heating the air. So the electricity or the heat energy is going straight into the pan and you're not losing all that heating energy around, which is super cool because you can cook without heating up your kitchen as much. Um, all electric commercial kitchens, just using that as an example. Yeah, there's challenges with it. A lot of it is unfamiliarity, but the more we talk about it, the less unfamiliar it'll be. Might be some first costs, same as anything else, right? Availability in multifamily, yeah, you do need stainless steel cookware. If folks have aluminum, that's not going to work, but that's not generally a tough change. A lot of benefits. I've talked about some of them: cooler kitchen, energy efficiency, improved air quality. This is big, right? So you're not just burning gas inside your kitchen and breathing all that in. So that's super cool. Might be able to reduce your ventilation requirements. And in some cases, smaller footprint for the equipment. Let's see, we've got about 10 minutes left. I do want to leave a few minutes for some questions. And I'm sorry, I'm getting kind of excited about these things and maybe talking a little more than I could. Elevators, I'll just say there's efficient options out there, and those keep changing too. So ask your elevator supplier. There are classes of energy efficiency. Some of them can qualify for incentives, so that might help, but ask the questions. A lot of information about traction elevators here, but there's a lot of different ways that you can improve efficiency. I'll encourage you absolutely to look at the options next time you're talking to your vertical transportation consultants. So we just looked at a ton of measures. There's a ton more out there. Keep looking. How do we evaluate them to make sure that they're right for our building? One way is to quantify how much energy you're using. Maybe you're using a tool through your software that automatically calculates the outputs, the carbon outputs. But even if you're not, there are formulas that you can use that help you translate X amount of electricity, X amount of gas into carbon emissions. So if you're using an energy model that gives you how much electricity and gas you're using, that's a pretty quick calculation. But most tools are starting to do that math for you. There are online calculators that can help you do that too. Really, it just comes down to, okay, how much fuel, how much carbon per unit of fuel equals how much CO2 gets emitted. That can get really complicated over the course of a day or depending on where you're at. Um, California, of course, fewer pounds of carbon emitted per megawatt hour of electricity. But look up the areas that you're working in and see like what their emissions factors are, because that can change the type of equipment that you might choose. Oh yeah, and here we are. The green that just circled is California's. So yeah, way down on the low end. if you're familiar with NREL, National Renewable Energy Labs, they have a bunch of really cool tools online here. This is just a screenshot of one of them. You can feed in data or customize charts that show you over time or different areas how much carbon different energy sources are using. Just Google NREL carbon data, and this will probably come up. It's referred to as cambium. It's a cambium data set. So if you want to write that one down, that'll be another one to throw into Google, and it'll help you get to these tools. They are free to some degree. I mean, you can do a lot with the free versions. Um, with them, the cambium data also shows, and I'm going to give you a quick little run through here. This is January on the left through July on the right, and then time of day, top to bottom. So this is kind of a heat map showing that, okay, in carbon per megawatt hour of electricity generated, like we saw earlier, the green is during the middle of the day when there's all that solar online, right? And the red is higher carbon emissions during the night when we're burning fossil fuels. Um, Carbon performance, another metric just to think about, cumulative tons of carbon emissions for your building. Like if you add up all the carbon emits from day one onward, this is just a quick study we did showing, okay, VAVs on the left, geothermal on the right. You can see how from back to front, the cumulative impact is incredible. The difference between a geothermal system, ground source heat pump, compared to a traditional, gas electric VAV system. So think about it cumulatively. Also, it can help reinforce the message that we might be trying to convey to our owners. All right, so super quick conclusion here, so I can answer at least a few questions. I'm cool to stay around a little bit late, but if you need to go, that's fine. Set your goals, electrify and decarbonize what you can. Remember, energy efficiency first, alternate energy and grid sources second. You want to reduce the energy you need before you supplement it with more energy, even if it's lower carbon. And then evaluate strategies with the right carbon rates, right? Higher electricity use doesn't necessarily mean bad now if that electricity use is low or zero carbon. And then make a commitment to implementing it. Then before I wrap up, I'm just going to share one last thought just to, I don't know, create a picture here. So start early, mix the concepts into the batter at the beginning when it's more cost effective to do so. And if you leave sustainability to the end, icing on the cake, it's easier to scrape it off in value engineering. So a little bit of a picture there for you. We don't want our efficiency goals to be scraped off in value engineering or whatever. When our decision making is happening fast and maybe we don't have time to be as precise. So, thank you so much for being here. And I think we do have at least a couple minutes, so I'm happy to answer any questions. I see there might be some in the chat. So let's see what that might look like. Oops, here we go. Okay. Sorry, I'm going to read off to the side here in the chat. Will the recording and slides be available? I think so. AIA, can you respond to that? Oh, you already did. We will post a recording. Thank you. How about solar thermal hot water heating? Yes. And passive solar heating shading? Absolutely. I didn't cover those today because those have honestly, they've been around forever and they're super cool. Keep doing them. You can use solar water heating to either preheat the water or as the main energy source. My focus today was on like some newer technologies of high performance measures, but those are absolutely things you should be thinking about if your building and your owner and your, any other constraints that you have can work within that. So yes, absolutely, please do. But yeah, just not part of the like newer technology stuff that I wanted to cover today. Good question though. Yeah. Um, Thank you. And if somebody wants to come off mute and ask me a question, that's totally fine too. Or type them in. I think I caught them all. Yeah. Good questions though. Info on 120-volt water heaters. I wish I had more to say about them right now. The experience that I have is with the more commercial systems. So, yikes, I would have to say do a little digging. Sounds like something I need to do a little digging on too. But anything like seriously, anything that's out there that you're finding that looks interesting, um, talk to the suppliers, talk to your, if your firm has a sustainability lead, talk to your plumbing engineers, mechanical engineers on the water heating side, find out what they know, but don't necessarily take someone's word for it because this stuff does change so quickly. And what might be, what might have been a inefficient 120-volt water heater a few years ago might be completely different today. So get out there and ask the questions, like be super curious about this stuff and always try to find like what's newest. That Google can be your enemy sometimes, but it can also be your friend to help you ask the right questions. Oh my goodness. How will MEGA's policies affect California regulations? So, um, for the time being, the regulations that are in place in California are California's, and the policies, the challenges that are coming out of the current administration. I mean, it's a totally different story, but you're kind of seeing it with the riot controls right now, where it's a bit of a battle between the state and the federal. But things like the California specific, I'm speaking about incentive programs now, because again, that's the world that I live in. Those are driven by California, and again, for the time being, there's not a whole lot the feds can do about that because they are driven by the state, by California's utilities, and honestly, by you all who are demanding this kind of stuff. Keep demanding it at the state level. Do what you can at any governmental level, but it's going to be a tug of war, not going to lie. Luckily, so much of this is happening at the state level that aside from things like the federal energy efficiency acts and programs, um, a lot can still happen at the state level. So stay involved. Let's see. Oh, yeah. Hang on a second. Let me look back through some of these questions and how much time. It's right at 3 o'clock. I totally get it if some of you need to drop off. I'll try to answer a few more of these. Um, yeah, okay. So 120 heat pump water heater. Yes, that's what I thought you meant. And the same still holds. I wish I had more to say on that. But what I mentioned, I still hold fast on. Keep looking into it, keep asking questions. All right. Had an engineer say we need to upgrade to 400 amp service, but I've seen others that say we can stay with 100 for full electrification. Oh yeah, the what gives is the big question there. Um, Keep asking questions. We do see, I mean, I'll be honest, with this shift from gas to electric, we do see a need for bigger services in some case. And my goodness, that's a whole other presentation on like the challenges with upgrading your transformers, your switchgear, all of that stuff. Um, even transformer lead times are longer in cases for higher amperage transformers. So I can't speak to that specific case, but if there's that big of a difference between 400 amps and somebody else saying 100 amps, try to engage, if you're not already, a consultant that's either familiar with those opportunities that might not be your electrical engineer, and just ask those questions. I'm going to keep saying that. Ask the questions. You don't have to take everybody's word for it. Don't be a jerk about it. But you can ask some interesting questions about where that data is coming from and see what you can figure out. ADUs need owner meter in California with 100 amp as the main. That might be in response to the other one. Yeah. And current status of IRA. Honestly, these things do change so rapidly. So personally, I would have to rely on Google if I didn't have like an immediate source that was totally familiar with it. I honestly have to go to others in my organization to ask for status on stuff like that because I'm off focusing on, specific buildings, and other people are doing more of the research on the policy shifts. So, connect with who you can. I really wish I had a better answer than that, but there's a lot out there. Try to weed through what you might be seeing on the news or on, not quite as legitimate news sites. But yeah, just stay stay vigilant, stay as informed as you can. Uh, keep questioning what's out there. So I think I'll wrap up there. If any of the AIA folks want to say anything in closing, I just want to say thank you again so much for being here. I love talking about this stuff. My contact information's on the slide if you want to contact me.
Yeah, thank you so much for coming and presenting, Rich. We really appreciate it.
Same.
Great. Have a good afternoon, everyone. Bye
Take
all.
care, everybody. Bye, all.